Hello, welcome to this presentation on mean value theorem. The mean value theorem as applied in calculus, and we're going to be looking at components such as implications of the mean value theorem, real-world examples or real-world applications of the mean value theorem, and then problem solving. So here's a statement of the mean value theorem, that if a function f is continuous in a closed interval ab and differentiable on the open interval ab, then there exists at least one number c in the open interval ab, such that f of b minus f of a over b minus a equals f prime of c. Diagram here shows us the illustration of the mean value theorem. This is a closed interval AB and the point C in the open interval AB, where this tangent line here has the same slope as the secant line. So let's see what the rate implications are and the geometric implications are. In here I have a diagram here which actually illustrates more than one C in the closed interval AB. And the reason we include the phrase at least one C in the closed interval AB. So for geometric interpretations, we say this expression here from the conclusion of the mean value theorem represents the slope of the secant line on the closed interval AB. And then f prime here represents the slope of the tangent line at the point C in the open interval AB. Then for rates of change implications, this expression here represents the average rate of change on the closed interval AB, whereas f prime of C represents the instantaneous rate of change at C. Now let's see some real-world applications here of the mean value theorem. First, we'll look at a road traffic scenario, and then a storyline to go with the traffic scenario. Then we have athletics, and we'll look at Usain Bolt's 100-meter dash in the Summer Olympics. So first, take a minute and read this narrative of interaction between a driver and a patrol officer on the highway. All right, so at the time the driver was clocked, it was only 60 miles per hour. And we want to know why should or can or would the officer conclude that the driver exceeded the speed limit. I say take note of this question. We'll solve it toward the end of this video, and if you get a minute, solve it, and then we'll compare our results at the end. So for those of us who haven't actually encountered any road traffic, I wanted you to see just a quick scenario of road traffic stop. Okay, my video is not loading too well. But once we see lights flashing on the side of the road, we know there's a traffic stop. And these are a few pictures that would indicate to you that, hey, you've done something wrong on the roadway and the cops are coming after you. All right, for athletics, we have the Jamaican sprinter Usain Bolt in his race in the Summer Olympics. And we want to know, could we use the mean value theorem by any means to justify that at some point in the race, Usain Bolt's speed exceeded 37 kilometers per hour. So let's see if our video will play for this event the summer 2009 Olympics. Not quite. So I'll play it from here. Okay.
World record holder Asafa Powell, American record holder, defending world champion Tyson Gay, world record holder and Olympic champion Usain Bolt, all racing for the gold medal in the footsteps of Jesse Owens. Usain Bolt has released the fix based on his first. There's the start, and Bolt got a good one. Engaged right with him, and so's Asafa Powell. Bailey's there too. But here's Bolt. Bolt charging to the front. Gay's coming, but can't catch him. Usain Bolt. Look at the time. 9:58. World record. I told you, Tom Hammond, we were going to see a 9:5 tonight. The wind is okay. In fact, ladies and gentlemen, it is into a headwind. There is no one on this planet or any other one that we know of that has ever run that fast. And now we get an update on the...
Okay, let's return to our slides now. So again, we'll see that problem again toward the end of the presentation. Here I have a guided practice. So find the values of C, or value of C in the closed interval 0, 4. That satisfies the mean value theorem for f of x given as square root of x minus 2x. So in this solution, we need to ensure that the hypothesis of the mean value theorem is satisfied, and then we can apply the mean value theorem. So with the hypothesis indicating the continuity on the closed interval and differentiability on the open interval, we apply the mean value theorem. F of 4 minus f of 0 over 4 minus 0 equal to f prime of x. And we solve for x, and we obtain our results for the value of c equal to 1. So at this point, we'll look at independent practice, which is what students will be given the opportunity to solve. If we go in here, we can solve for the value again in the open interval to 6, and we want to verify that f prime of 4 is actually approximately equal to the average rate of change of the function containing the number 4. So we look at this interval here and we find that 4 is in between 3 and 6. So we could use 3 and 6. Those are the closest values to 4 from the left and from the right. And so we verify that the hypothesis of the mean value theorem is satisfied here. And then we plug into our average rate of change, and we use that to approximate the derivative of the function at 4. Next, this is another practice when we find the value of C, or values of C in the closed interval 1, 3. So again, the hypothesis of the mean value theorem is satisfied. We take the derivative, and then we take the average rate of change, set them equal, and our result is 4 over natural log of 9. Then the practice 3 here is where I would give you the opportunity to solve the traffic stop problem and the Usain Bolt problem. Take a minute and look at those problems again. So here's my solution to the traffic stop problem and Usain Bolt's problem. So we say the average rate of change of the 30-mile trip would be the 30 minus 0, and then the time in hours, time change in hours, which gives us approximately 64.3 miles per hour. Now with this result, we can then justify why the mean value theorem is applicable. So we say the mean value theorem guarantees that there was at least one instant during the trip when the average rate of change equaled the instantaneous rate of change. Hence, at some point, the driver exceeded the 60 miles per hour speed limit by driving approximately 64.3. Also, we have Usain Bolt's solution here. So the average rate of change of Bolt's race is given as below. So we convert values into kilometers and into hours, which gives us 37.6 kilometers per hour. So we conclude here that by the mean value theorem, there was at least one instant during the race when the average rate of change equals the instantaneous rate of change. Thus, Bolt's reached a speed of 37.6 kilometers at some point in his race, which leads us to confirm that Bolt's speed exceeded 37 kilometers per hour. Thank you for watching, and as always, have a good time.